Welcome. My name is Holly Anderson, and I'm going to be the speaker talking about regularities and laws. The first episode that I put together for these videos is kind of a potted history that gives some background in terms of how we got to where we currently are with respect to laws. All right. So the approach that I'm going to be taking is one that's sometimes called complementary science, sometimes called integrated history and philosophy of science. And it's a way of sort of zooming out from a current discussion in order to situate it in a longer historical trajectory than is often taken to be the case. So this video is kind of the very compressed view of a lot of what I take to be interesting historical moments, not considered in a really historically conscientious way, but where I'm sort of going back as a philosopher and kind of picking out the parts that I think are really useful or interesting. If you'd like to read more about that, there's a really fantastic book called Inventing Temperature by Hasok Cheng, in which he kind of both introduces what he calls the complementary science approach and also illustrates how to do it by performing it for the case of the thermometer. All right, so the videos that I'm going to be putting together, this one is going to be what I'm calling a potted history. So we're really taking a super compressed view and just taking bits and pieces that I think are going to set us up in a good way for discussions further down the road, or that are sort of interesting highlights in their own regard. So we're going to then cover like 2,000 years worth of material all the way through the 20th century. The second video is then going to take up some of the questions that arise in this one, in particular mathematics as a distinctive language in which to describe regularities that have modal content. So that video is going to have sort of two parts, one of which we're going to look at the back and forth between two physicists, actually, and see what they have to say about it. And then we're going to look at some contemporary discussions about distinctively mathematical explanation and what it is that mathematics is doing in those cases. And then the third one takes up the contemporary discussion about laws as a description versus as an explanation in the context where there was a real movement away from the use of laws for a long time and the introduction of different kinds of avenues for explanation, so mechanisms or causation. That will be in the third and final video. All right, so some terms that might be useful for us to have on the table. Regularities here is going to be used pretty loosely. There isn't anything really specific about it. Mostly it's that there are discernible patterns, what are often called phenomena, that can be re-identified in different times and places. So these don't have to be particularly complicated, just, wow, when I drop a rock, it always falls and it always falls straight down. That's the sort of thing that can count as a regularity. So it's just the sort of catch-all term for the ways in which we discern order or similarity between different parts of the world. So if there's certain kinds of events that reliably follow each other, then we call that a regularity. So it can be really specific because there might be some regularity to how dropped rocks fall. And then it can also be more general in the sense that there might be some regularity that we now want to talk about. That's just how all objects with mass behave in gravitational fields. So we can sort of pack more into that regularity. So one of the features of regularities is that they're often robust to perturbation. So a regularity often holds despite attempts to disturb it. And they're often specified according to which the conditions under which they hold or the conditions under which they fail to hold. So there's something about it that has to do with how reliable or stable or sturdy is this particular regularity. And the term laws, similarly, is going to go through some massive changes in meaning. But it's often used loosely to pick out a description of a regularity in terms of this modal content. So what had to be or what couldn't have been. So these ideas of necessity and impossibility go under the idea of modality, and laws are often the way of describing a regularity such that you're imputing to it some degree of sort of modal strength. It didn't just merely happen, it had to happen. So for that reason, we think that laws as descriptions, they're often treated as stronger than descriptions of things that are true, but merely true for accidental or coincidental reasons. So one of the classic examples for this is, it might be true that all of the coins in my pocket are silver, so I don't have any pennies in my pocket. Nevertheless, we don't think this is a law. And if we're pressed on it, we might say things like, well, if I took a penny and put it in my pocket, that would be totally fine. There's nothing about my pocket that somehow excludes pennies. However, in another classic case that we'll get to at the end of this video today, there's no spheres of gold larger than 1 kilometer in radius might be true. And it might also be true that there's no spheres of uranium that are larger than 1 kilometer in radius. And yet we think they're true for different reasons. So you could, if you really wanted to get around to it, build such a sphere that's larger than 1 kilometer in radius. So it's just kind of practical considerations that stand in your way. On the other hand, you cannot build a sphere of uranium. So there's something impossible about the second case that it just happens not to be the case for the first. So that kind of difference is often one that's pointed to as where the first is accidentally true and the second is true for some sort of law-like reason. All right. And the tradition that I'm going to be looking at historically is often called natural philosophy. And the laws in natural philosophy are also often characterized by being surprising in some way. So they're surprisingly simple, given some really complicated set of phenomena, or they're surprisingly elegant in some mathematically nifty way, or they allow for us to discern some sort of surprising or unexpected sort of simple pattern of regularity beneath a lot of other phenomena that don't seem to have any kind of regularity to them. So there's something about laws in the natural history discussion where they're going to be sort of surprisingly simple or straightforward. All right. So one of the other things that's worth mentioning at the beginning is that there will be this ongoing interplay between words and world on the two hands. So often when you're doing science and doing it for the first time, we'll see the very difficult thing is figuring out how exactly to describe a regularity. There's something regular going on, but what is it? Like, what are the terms that you should use? What are the things that really get at it? So there might be things that are regular that are just a consequence of something more fundamental going on. You want to figure out what's really the best way to describe it, and that includes what is it that we should ignore that might seem to be very salient, but will turn out to be not particularly relevant, might even just be noise or something like this. So the term law, as it gets used, is often ambiguous between these two, although as we'll see, sometimes people take it to be more one or the other. So laws neutrally can be the description of a regularity in the world, where the laws are the description. So you give a kind of statement in words about something over here in the world that has a certain kind of regularity. On the other hand, sometimes laws are used as the thing in the world thusly described. So you've got a mathematical description of a law, but the law is somehow like in the fabric of the world, or it's like making stuff happen out there. So there is this interesting ambiguity that people sort of, make hay with through the history of science between laws as descriptions of something in the world versus laws that are features of the world that we can then describe using some language, potentially mathematics. All right. So some overarching themes that we're going to get to. It should be pretty clear. Mathematics as a language in which to express laws. That's going to show up in today's video, and it's also going to show up in the next video to a very high extent. There has always been this philosophical fascination with geometry, and we could do just an entire video or whole discussion on why it is that philosophers have been, for a very long time, so fixated on geometry as somehow like the highest of the mathematical sciences, such that if we could only emulate what they're doing, then we would have like the strongest or the purest or the best form of knowledge. But we're going to see how we start with a, sort of a geometric, like purely geometric set of laws, and then we move to something like numerical precision, and then we move to something like logic, which will have a very different form than the mathematically formulated laws. But then we kind of move back to mathematics again. The other thing that comes out of looking at the history of laws in natural philosophy is that laws are often what I'm calling a locus of inferential connections for some sort of theoretical system. So you have a system of physics, perhaps, where there's a few key laws, and they're designated as laws because they serve especially important purposes for relating how different quantities will change when other quantities change. And so you're able to use these laws to draw inferences about what to expect under different kinds of circumstances. And you might have different laws, all of which have the same quantity in it. So mass might appear in several different places, and velocity might appear in different places, but here in a squared term and here not. So laws often serve as this kind of locus of inferential connections to make a package, a sort of theoretical package, hang together in a systematic way. We're also going to look over the distinction between what are called phenomenological laws versus unificatory or fundamental laws. And we'll have plenty of time for that in the video. And then we'll sort of touch on this today, and it's going to launch us into the discussion for the third video, describing versus explaining the regularities that we find. So what is it that laws are doing? Are they merely encapsulating in a particularly efficient and precise way a description of the regularity? Or does that kind of mathematically formulated precise description thereby explain the regularity in some way or another? And then how does the explanatory role of laws fit with respect to mechanisms that will explain in a very different kind of way, and causation that explains with a very different kind of modal implication? All right. And so we have this kind of like set of terms that are going to be showing up. So explanation is really a key thing here. When we're describing regularities, when we're talking about generalizing from one set of circumstances to another. So when can I say, oh, a law holds here, but I think it will also hold over here? How are we using these for prediction? And especially, how are we using them for control? How are we using them to bring about states of the world that we want to be there? All right, so we're going to begin with Aristotle and Aristotelian physics. So Aristotle, in the kind of broadly Western orientation that I'm taking in the sort of natural philosophy approach here, developed laws of motion that essentially involved the essences of substances. So you have different kinds of substances out of which the earth or the cosmos is made. Two of them are earth and water. And it is in the essence or the nature of those substances that they have a certain kind of natural motion. So Earth has a natural motion towards the center of the cosmos. Water does also, but not as strongly as Earth. That's why you get the water on top of the Earth. Air has a natural motion upwards, away from the center of the cosmos. And similarly, fire has an even stronger upwards motion away from the center of the cosmos. And then, of course, outside of this sublunar realm, so everything below the moon, things are made out of ether. And ether is this fifth substance that has a different natural motion, which is circular. So everything is made out of one of these things, and these each have their own natural motion. And so you can get certain kinds of lawful descriptions. So you've got what there is and how it moves and why it moves that way, because it's in the essence of the substance itself to do so. And so you then have like the material to make explanations for why things behave in the way that they do. So we can explain why the fixed stars go around in a perfect circle, because they're made out of ether, and ether moves in a perfect circle. You can also point then to the need for further explanation. So if you see a rock come sailing through the air sideways and then hit the ground, you know that there was something that imparted that violent motion to it, because rocks don't on their own move that way. They move downwards. So it sort of sets out what the boundaries of the world are, such that you can explain things. And then the laws are describing the parts that are necessary. So accidental or violent motion isn't lawful or law governed, whereas the necessary motions or the natural motions are lawful or law governed. So you can't make Earth permanently do the things that it can't do. And so here's Aristotle on this. We think we understand a thing simpliciter, and not in the sophist sense accidentally, Whenever we think we are aware both that the explanation because of which the object is its explanation, and that it is not possible for this to be otherwise. So in order to understand something, in order to have an explanation of it, he thinks, you have to know that this is the explanation. So you have to have gotten onto the right thing. And that right explanation has to say that it had to be thus, and it couldn't have been otherwise. So you can really see the modal force that's embedded in this way of understanding it. So there's a way in which Aristotle is developing these mathematical laws, but they're ones coming from what we might call pure geometry. So he's not saying things like the rate at which rocks fall is so and so many units per unit of time. Instead, it's sort of proportional. So in the way in which Euclidean geometry gives you proportions of how different shapes and angles relate to each other, similarly, we have the laws of motion involving proportional relationships. So the rate at which Earth falls towards the center of the cosmos is proportional to its weight, and it's inversely proportional to the resistance. So insofar as it gets heavier, it's going to fall faster. Insofar as it's falling through a medium with more resistance, it's going to fall more slowly. This isn't specifying any kind of a numerical speed, so it can fall slower through oil than through air. And in both cases, it's still falling proportional to weight, but measuring a specific speed at which it was falling just wasn't the kind of business that they were in when they were doing these kinds of laws. So they're just sort of this purely proportional thing. But you can really see how part of what's involved in giving laws of this form is this built-in conceptual structure. So you've got a set of conceptual categories that you're using to carve up these apparently regular phenomena that you see so that you can then say how they relate to each other. So the concepts don't sort of free float. So you don't just have water as this thing that you can talk about all by itself. You talk about water as one of the essences that, or one of the substances that has a certain kind of essence, and how they relate to each other. So you've got inferences between these different categories, things like natural motion and the substances. And then the lawful relationships among the categories give you a handle on how to use those categories. So you need more than just the categories, you need the ways in which they're lawfully related so that you can make inferences in order to predict what you might see in different circumstances. So if you've got something that's even thicker than oil, you can predict that your rock will fall even more slowly through that than when you drop it in the barrel of oil. And you can use it to explain. So you can explain a lot of things about the way in which things behave using these kinds of conceptual categories and the ways in which they're related to each other. And this will become a big theme as we go all the way through the contemporary era. That's why we're using Aristotle to launch it. The very concepts that are being used here build in certain kinds of assumptions. So you need to be able to individuate a quantity in order to lawfully relate it to some other quantity. So for instance, the idea of velocity in physics just has no place in this conceptual categorical scheme. So you can't translate things like Newtonian mechanics that talks about, say, changes in velocity into the Aristotelian scheme because there just isn't anything that could stand in a meaningful way for those categories. So you have to use some sort of conceptual structure, but every time you do, it's going to come with these sort of assumptions that are built into it that carry baggage with them as well. All right. So, for example, let us first decide the question of whether the Earth moves or is at rest. For, as we said, there are some who make it one of the stars, so it goes around in a big circle, and others who, setting it at the center, suppose it to be rolled and in motion about the pole as an axis, so having a daily rotation. That both views are untenable will be clear. I take as our starting point, are untenable will be clear. If we take as our starting point the fact that the Earth's motion, whether the Earth be at the center or away from it, must needs be a constrained motion. It cannot be the motion of the Earth itself. So the natural movement of the Earth, part and whole alike, is to the center of the whole, whence the fact that it is now actually situated at the center. So here we see Aristotle making one of his, what he took to be his strongest cases against the idea that Earth was either rotating on a pole or going around in anything resembling a circle, because any such motion would have to be essentially imparted to it. So you would have to throw the Earth or pieces of the Earth, or, cause them to be put into a spinning motion, because Earth by itself doesn't do that. So you have the conceptual category doing the work for you, where the very nature of Earth is that it is not a thing that could be in motion. All right, so this sets us up as we're going to sort of skip some more centuries in the meantime. By definition, there's nothing that we could now know as a planet. If by planet we mean something like a heavy body, a massive body that's in orbit around the sun. So Earth could not be a planet because it can't move like that, because Earth can't move in circles. And nothing made out of ether could be a planet. So the things that move in circles can't be made out of mass, if by mass we mean something like Earth. So ether moves in perfect circles, and it has to go around the center of the cosmos. So the way in which they've described the regular patterns of motion and what makes them necessary rather than merely accidental means that it's just conceptually impossible for the Earth to be in motion. All right, so we then sort of pair this in the next couple centuries with developments in Ptolemaic astronomy. So Ptolemaic astronomy added some new mathematical infrastructure to the Aristotelian physics so that they could get much more numerically precise predictions, not merely proportionality claims, but really precise predictions about where to find certain astronomical bodies at certain times of, the day and the year, etc. So now there's new notions of numerical precision. But even with this new standard for empirical adequacy, so you make a specific prediction, you should be able to go out and check and say, okay, is that where I did in fact find Venus on that particular day? It's not universally expected that Ptolemaic astronomy is providing what we might call a realist description of what's actually going on. So a realist description is one that describes like the real paths that it's taking. It's understood that it's providing something like a mechanism for making predictions, but not necessarily by having captured the exact motions of everything up there. So here's where we skip some more centuries. So this brings us up to the Copernican. The start of the Copernican revolution really kind of, comes after Copernicus. But when he published his book, there was this disclaimer about realism versus instrumentalism. And what he wanted to say is, well, I'm offering you this new picture of the world in which Earth goes around the sun rather than the sun going around the Earth. But hey, I'm not saying that's how it really is. I'm just saying this is much better for doing your calculations. So he sort of gave this disclaimer. This is merely an instrument for prediction. It's not a realist account. And so there's this really interesting question. Ptolemaic astronomy has really been refined. Should it then be replaced? Is it in fact merely this mathematical device for predicting locations? If so, there's no need to really replace it because it's not making any claims about the world. Or is it supposed to be an accurate description of what actually is happening up there? In which case, a realist view would be better than a non-realist view. So if you had a realistic description versus this mere calculational device, and they both make the same empirical predictions, one of them's easier to use, but also seems to be describing real motions, there are a lot of reasons to think that you should prefer the realist description of what's actually going on. Because realism in this context would be a way of describing the regularities that more accurately captures the modal content of what conditions it holds under, when you might expect it to fail, with what degree of necessity does it actually hold, and when can I generalize it? So if you have a merely instrumental device for making predictions, there's no reason to think that it would continue to hold if you sort of moved it to a very different context. Like if you discover a new astronomical body, you can't fit it into that. You have to sort of work it up by scratch. Whereas a realist view would give you a place in which you could fit it so that you could see if there is a new astronomical body, I can also say how it would behave. So those are kinds of the kind of grounds that would cause you to want to be a realist about your view. So in that sense, a law that's empirically adequate for prediction and also realistically accurate would be better because it captures these other features. All right. So Galileo and the people who are working contemporaneous to Galileo were sort of pushing this Copernican revolution forward. And they needed new phenomena in the sense of they needed new ways of identifying what is it that's actually regular in the world. So when you discover that really you can't make the Aristotelian system work anymore, what that means is that you no longer know what conceptual categories you should be using, such that you could use those conceptual categories to look for lawful relationships among some of the categories. So you need new conceptual structures in addition to new laws. So what are the kinds of quantities that we should be measuring such that if we measure them, we will find something regular in the world that has modal features. So what happened then was really interesting. So a lot of people were working on this. And again, this is just a very kind of European-centric view of what was happening that we're using to illustrate a lot of these ideas about the laws that we're going to work with later. So what happened was the discovery of a lot of what are called phenomenological laws that are very specific. Let's see. Oh, well, we'll get into the phenomenological laws. So instead of trying to look for one grand universal law that holds everywhere and at all times, Galileo managed to make some important discoveries about patterns of regularity in objects that are falling close to Earth. And then separately, Kepler, for instance, managed to find some very striking mathematical regularities in the exact trajectories that the planets take around the sun. One of the other things that happens here is that there's this sort of struggle in a religious context against this view that Latin was the language that ought to be used to describe the world. So both Galileo and Kepler were trying to argue that really mathematics is something that we should be using, and this wasn't, something that you should be worried about. All right, so this allows them to then identify these new regularities that could not be accounted for. As soon as they started using telescopes for astronomical observation, you found all sorts of stuff up there that had no place in the Aristotelian and Ptolemaic view, and you had no clear way to stick it into that view. So it sort of heightened the need for no, really, why don't we just start over and do something different? And I think this episode really helps us see, so when we go from Copernicus through to, say, Newton, the interplay between revision of the concepts that are being used, the innovation of how to measure the quantities that we're now using as the concepts, and then how new developments in mathematical representational power allowed them to make claims about how those quantities related to each other that they couldn't have made before. So you can state something more precisely when you do things like have calculus on the table. All right. So this led to some really great innovations by which both time and space, so like temporal measurements and spatial measurements, were sort of rendered more tractable for mathematical description. So you already have somebody like Descartes who's come up with ways to, excuse me, combine geometry and algebra by, the innovation of being able to plot a graph. And so there's a certain kind of shape to a motion, but also you can give an equation that yields that shape. And so being able to talk about the shape of something like this and the equation that gives rise to it was an incredibly powerful move forward, such that it's now easier to talk about how you're going to geometrize and make more numerically precise the measurements that you're doing in time and space. So this is a picture from the inclined plane experiments. And I find these very clever because, back then you didn't really have a stopwatch that you could use if you wanted to measure how fast does a ball roll down a plane. And you're rolling it down a plane because that's a way of letting it fall that's slower than just dropping it. So you can see more about it. It's still falling, but you can make it fall more slowly when you put it on an inclined plane that can change angle. And then that it goes faster at the end than at the beginning, but by how much does the speed of the ball change in different increments of time? Like how much is it? I'm trying to avoid the word acceleration because it's anachronistic, but really how much does the ball speed up as it falls. And so he was able to do things like you can put little markers on there that make a tick sound when the ball goes by, and then you space out your markers so that you can hear. You don't have to have a single unit of time. You can just have even units of time. So we've still got this kind of mix of geometric proportionality in there where you have even units of time, and then you can measure the proportion, like proportional differences between, oh, in the first unit of time, here's how far it rolled. In the third unit of time, here's how far it rolled. And you know that they were even units of time because you could hear the clicks as the ball went by. So it's a very clever, I think, experimental innovation. All right. So this allows him to come up with, here's an example of one of these phenomenological laws. It's called the law of odd numbers. So he says that the distance fallen in a unit of time is proportional to time squared. So you can see a little sort of chart or graph here. So in the first unit of time, it falls 1 unit. In the second unit of time, it falls 3 units. In the third unit of time, it falls 5 units. In the fourth unit of time, it falls 7 units. And so what he found is that for each moment, it went up by odd numbers. So you've got 1, 3, 5, 7, and then it will keep going 9, 11, 13 for how far it falls in each unit of time. And then you can sort of add those up. How far has it fallen total? So after 2 units of time, it's fallen 4 units total. And you can see that after 2 units of time, you square the 2 and you get the 4. After 3 units of time, it's fallen 9 units total, and the 9 is 3 squared. After, 1, 2, 3, 4, sorry. After 4 units of time, if you square that, it's fallen for 16 units total. So there's several really striking mathematical, sort of simple mathematical regularities going on here. One is that the total distance fallen is just the square of how many units of time have been going on. And the other is just that the amount that it falls in each given unit is going up by odd numbers. So there's no reason that you should expect that. So when you see something like this, you think, aha, there's some kind of like, this is a key moment. All right. He also discovered that you could decompose motion. And I do think Aristotle would have liked this one, but it doesn't fit with Aristotelian motion. So we've got this distinction between violent and natural motion, which just wasn't precise enough. What Galileo discovered is that if you drop something and if you throw something at the same moment, then they both hit the ground at the same time. So traveling horizontal to the ground, how far you're traveling is independent of how fast you fall. Everything falls at the same rate, regardless of its motion in this opposite direction. And so that's also a surprisingly simple way to be able to talk about like the trajectory of a cannonball. Namely, there's its motion that direction and its motion this direction, and you can just decompose it into those, out of which you get this complex shape. All right. So one of the other key things that Galileo was in a good position to do was to show that there was some plausibility to the idea that the Earth was in motion. So he didn't manage to really firmly make the case that Earth was in motion. What he did instead was open the conceptual possibility that this isn't like in principle impossible. So he was able to show that if you think about inertial reference frames where you're neither accelerating nor decelerating, he says all experiments that you perform in there, like looking at the period of a pendulum, are indiscernible as to whether you're, for instance, moving smoothly on a boat or if you're just still on the shore. So you will always get the same results. And thus, none of these experiments about falling sort of tell you whether or not Earth is in motion or at rest. And that might sound kind of weak. Sometimes when I introduce this to students, they're like, well, but that doesn't show that the Earth's in motion. But it was a really big deal to be able to show that it was even possible that the Earth could be in motion, and that if it were, it wouldn't be obviously in conflict with our everyday experience. So that was a big conceptual innovation. And it shows something about the laws by showing us the conditions under which they'll not vary. So if you're doing it in a case where there's no acceleration or deceleration, you'll get exactly the same results. If you don't get those results, it's because something was accelerating or decelerating. So it gives you this kind of extra handle on things. Okay. So Kepler also came up with 3 laws that were just about planetary motion. We're just going to skim through these because it really doesn't matter. One of them that was a hugely important one is that he finally broke free of the Aristotelian obsession with circles. Even Galileo was sort of stuck in that. And he came to the realization that the planets are moving in elliptical orbits, which are different than just squished circles. So they have 2, what are called, they're called 2 foci. So here's one focus and there's the other focus. And the sun is at one focus of the ellipse for every single planet. So being able to say definitively what the shape is and that's where the sun is really important, because it then would let you say, what if there were another planet? What would its shape be? It would be exactly like this. So you get this extra modal content to it. The other surprising thing, a line, if you draw a line from the planet to the sun and you let it sort of sweep out area, it sweeps out equal amounts of area in equal units of time. So even when it's closer to the sun, it then moves faster. And when it's further away from the sun, it moves slower. And it always works out exactly right so that it's sweeping out exactly equal areas in equal units of time. And that's sort of unexpected. So even if it's moving at different rates at different parts of this elliptical trajectory, it's really nifty that it would happen to work out to exactly what it needs to be in order for those to be sweeping out equal areas. And if you know any, calculus, you can really see how this is setting us up to get into the, well, how could we find out what that area is as we're going? So we're looking for integration here. And this one is my favorite just because it's really random. So you take the length of each planet's own year and you square it, and it is directly proportional to the cube of the average distance from the planet to the sun over the year. So there's something about how long the year is that's consistently related to its distance from the sun. And if you square this one and cube this one, you always get exactly the same number. So it took him a very long time to find this, as you can imagine, because there's just so many possibilities. Like, why would the planet's year, rather than some other kind of unit of time, be what's at stake? Why is it the mean distance rather than the shortest distance or the longest distance? And why square one and cube the other? And then the fact that there was any kind of a mathematical consistency among these was really striking. All right. So you have this sort of like system of Aristotelian physics that's now just completely fallen apart. It doesn't work for motion close to Earth, and it doesn't work for motion in the heavens, the sort of superlunar realm. And that means that you have to sort of reject all of the conceptual categories and come up with everything sort of anew, because you no longer have any explanatory resources. You don't have any laws. You're not sure what you're supposed to formulate them in. So the whole system kind of hangs together or falls apart together. And so they need these new laws of motion that require new descriptions and new mathematical techniques and new mathematical shapes, such as the ellipse, by which you can talk about what exactly the regularity is. It's not just that it goes around the sun. It goes around the sun exactly in the shape of an ellipse with the sun at one focus of the ellipse. All right. This is from Kepler. Humanity will realize that God, who founded everything in the world according to the norm of quantity, has also endowed humanity with a mind which can comprehend these norms. For as the eye with color, the ear for musical sounds, so is the mind of humanity created for the perception not of any arbitrary entities, but rather of quantities. The mind comprehends a thing the more correctly, the closer the thing approaches towards pure quantity as its origin. So he's really trying to get people to move away from Latin and using this, but we were created in order to understand the mathematics that was also created as the sort of guiding feature of the world. So this one is from Galileo. Philosophy is written in this grand book, the universe, which stands continually open to our gaze. But the book cannot be understood unless one first learns to comprehend the language and read the letters in which it is composed. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. Without these, one wanders about in a dark labyrinth. All right, that's from the Assayer. So this brings us up then to what's called the Newtonian revolution. I'm going to put the word Newtonian there because Newton gets a lot of credit, and he did some really important stuff, but he was definitely not the only person who was working at bringing this all together. So they now have the ability to combine these different kinds of representations to give new expressions so that you can describe a shape using a mathematically precise algebraic expression. So that was a huge move. Thank you very much, Descartes and other people who worked on this, because then you're giving a realist description of a trajectory of motion, and you can make it numerically precise using the algebraic equation that you've now developed to go along with it. So that was a huge breakthrough. And now you can come up with new quantities that are the right ones to keep track of in order to give you this shape right here. So you've got this new system of laws that's emerging, including this package of equations with definitions and terms and quantities that are all sort of inferentially connected to each other. So they all kind of hang together. And once again, we're now getting to something that's intended to be complete as a system. So Newton's package is supposed to be complete the way that Aristotelian physics was, not Kepler, not in the way in which Kepler and Galileo were offering phenomenological laws about very specific kinds of phenomena. So it's trying to do fundamental laws instead of merely phenomenological ones. But part of the power comes from the unification of those phenomenological laws as different instances of the same underlying more fundamental laws. So part of what was really powerful about the Newtonian revolution, which is why it's called the Newtonian synthesis, is that there were such good and precise descriptions of motion close to Earth and motion of astronomical bodies that once you invented some new mathematical techniques for talking about it, you could show how both of these were just the ways in which heavy bodies behave in a gravitational field. So you can now unify these previously very disparate realms as different instances of the very same underlying laws. So he unified all these phenomenological laws as special cases of this more general kind. All right. And this systematicity isn't just like a, philosophically convenient thing. It actually guides people as they're trying to refine what comes to be known as Newtonian physics. So you don't get Newtonian physics from Newton. It takes at least, 100 to 200 years to sort of clean it up and make it hang together inferentially in an adequate fashion. So a really good example of this comes from Emily du Châtelet, who was trying to teach this physics as a tutor and discovering that really there's some inconsistencies in here. So she was in a position then to use the fact that it was supposed to be systematic and complete to essentially distinguish between momentum and kinetic energy. And everyone could recognize this contribution as not disagreeing with Newton per se and not trying to offer a replacement for it, but just there is a system that we're clarifying so that it all works a bit better. So energy is 1/2 mv squared, and momentum is mv. And so you can see that they both involve mass and velocity, and that's it. But one of them is just a linear equation. So momentum is just a line, essentially, whereas the kinetic energy has a squared term on the velocity. And in particular, this lets kinetic energy sit there as a thing that you can then differentiate and get to these other sorts of forms. So you've then got, so if you differentiate let's see if I put this up here. Yeah, we won't go through the differentiation. But this is a really subtle distinction that she was in a position to make because it was supposed to be complete. And because you now have the categories of mass and velocity that are sufficiently solid as ways of sort of grasping those parts of the world that you can make this distinction and figure out that you have to have a difference between kinetic energy and momentum. So what's really interesting is that a lot of stuff in here isn't clearly a definition or a law. Sometimes you can treat this as a definition and then other things become laws, or you can treat it as a law and then you make sense of it by this now being a definition. part of the goal of seeing this is that the role can change depending on what it is that you're doing with the whole system and what kinds of inferences you're making around this whole structure. And so I think getting to, once again, looking ahead to the third one in particular, I think there's a lot of reasons to be a sort of pragmatist, a philosophical pragmatist about laws. And really, a law is a thing that serves a certain kind of role in a theoretical package. So a law is a thing that you do certain sorts of stuff with, and it's especially useful because of the inferential roles that it plays, connecting these quantities to other things. So you really have to sort of evaluate it in the context of the entire theory or, model that it's part of. All right, so this brings us then to the growth of the sciences. Newtonian physics really quickly becomes the model of what science should be. So everyone, including like Kant, were, yes, this is exactly how we should be doing stuff. And it's the template for what laws should look like. They should be complete. They should be fundamental. They should be universal. They should hold everywhere at all times. And they should be necessary. So if it's not necessary, if it just happens to be true, if it's contingent, then it's not a law. So this really shaped the worldview, not just in natural philosophy, but in other parts of philosophy as well. And there's still a lot of ways in which you can, we could explore this, especially in the context of looking at time, and how we model time in physics and outside of physics, where there's this worldview that comes out of it, where there's just this deterministic manifold of events. There's just like sprinklings of things that happen in space and time, and they're connected by these laws that force it to be a certain way rather than otherwise. And everything is just kind of deterministically governed through time. And then there was a certain kind of starting point. And then once you have that starting point, the laws just make it be one way and only one way. Oops. Oh, yeah. This is what's often called the Laplacian view, where you just add the initial conditions, or you just take a time slice at any moment. And if you just fully specify where everything is and what direction it's moving in, then you can just completely calculate everything else. All right. So the synthesis itself, how you start with this process of developing phenomenological laws that are very clear and precise descriptions of phenomena, and then trying to unify those in terms of underlying regularities, is a pattern that people try to explicitly emulate. So Darwin was trying to do this, and he was drawing on geology and biology as sort of the serving the equivalent role for phenomenological laws that he was going to sort of bring together into this sort of cohesive theoretical package. In the meantime, geology itself was trying to establish itself as a science because it was formerly considered merely natural history. And it was considered merely natural history because of the contingency of the events that it describes. And it argued for itself. People argued that it ought to be considered a science by trying to argue for the ways in which geology is trying to uncover what's necessary about what actually happened, not merely what happened. So it's not just a telling of the tale of this happened, then this happened, then this happened, but it's really why it had to be thus and not otherwise. So it's trying to convey modal information as well. And then there were further achievements in this style that really made a deep impression on a lot of people. So beginning with the phenomenological laws, they discovered lots of specific things about electricity and magnetism. And then you have people like Maxwell, who then unify these into just 4 incredibly elegant mathematical equations for electromagnetism. And so this also looked like a slightly smaller version of the Newtonian synthesis, where you take these, who knew that electricity and magnetism would have anything to do with each other? And yet you can see how they're now different manifestations and different conditions of the same underlying laws. So that really caused a lot of people to get very excited, like, no, really, this is the way we should be doing science. So in, say, the late 1800s, this really becomes known as like the method of the sciences. Whewell, for instance, who was, I think, often counted as one of the first, people explicitly doing philosophy of science rather than natural philosophy. So he says, inductive truths are of 2 kinds, laws of phenomena and theories of causes. It is necessary to begin in every science with the laws of phenomena, but it is impossible that we should be satisfied to stop short of a theory of causes. In physical astronomy, physical optics, geology, and other sciences, we have instances showing that we can make a great advance in inquiries after true theories of causes. So Whewell is not merely noting this historical trend, but he's using it as sort of a methodological exhortation. So if you have discovered the laws of phenomena, you're not done yet. He's calling them theory of causes. As we'll see, the term laws and cause get used in really shifting ways during this period, but he wants you to keep going until you figure out what's going on underneath those laws of phenomena. And Poincaré also is often taken to be one of the first philosophers of science, and also took mathematics as the language that it was really important to express hypotheses in, precisely because experiments give us unconnected points, he says. So we've got this one and this one and this one, but we have to generalize them. So connect the points into a line by using mathematics. So he says the experiment will never give us all of the points to make up a line. You always have to connect them using mathematics. And in order to generalize like that, you have to have reason to think that these are the laws rather than some other way that's slightly different of connecting them. All right, so, and this is from Poincaré. I may be permitted to compare science to a library, which must go on increasing indefinitely. The librarian has limited funds for his purchase, and he must therefore strain every nerve not to waste them. Experimental physics has to make the purchases, and experimental physics alone can enrich the library. As for mathematical physics, her duty is to draw up the catalog. If the catalog is well done, the library is none the richer for it, but the reader will be enabled to utilize its riches, and also by showing the librarian the gaps in his collection. That is the role of mathematical physics. It must direct generalizations. All right, so this leads us to the 20th century, where we've got physics and philosophy of science on laws. So I'm going to do a kind of summary before we move into the 20th century. So at this stage, laws involve mathematics in some sort of crucial way. So they're important for expressive power, such as being able to perform derivations and integrations on equations. And they're really important for the precision in formulating functions that relate specific quantities, so that you can set up a situation where these quantities take these values, and then you measure the remaining quantities value to check that this is the correct equation in order to relate these. So you have these opportunities for new kinds of inferences and for empirical verification. We have this idea that laws are part of a package that hangs together, so that the terms that appear in one law also appear in others, and you sort of make this web of connection between them. And that's part of how you use the package in practice. So you can set up an experiment and use it to check various different things. You can use mathematics to draw generalizations that will tell you where to spend your precious librarian resources to go do an experiment over here. You shouldn't just randomly experiment. You should make sure that you're doing a good one. All right. We also then have the development of measurement devices that go hand in hand with the development of these new mathematical techniques and the refinement of conceptual categories for the quantities that could be lawfully related. So for instance, I didn't have time to talk about it here, but there's really interesting developments in thermodynamics. But in order to have those developments in thermodynamics, you had to have things by which you could, for instance, consistently measure temperature. And that's no small feat. What is temperature, such that it is one consistent thing that you could measure it? And when should we distinguish between like certain kinds of radiation and temperature? For this, I send you to the Hassok-Chang book, which is a very interesting read. But it's important to note that you can't come up with a measurement device for an ill-defined quantity, or you came up with a measurement device and now that just is the measure, like that's the quantity you're going to be measuring because it's what you have a measurement device for. So there's this really interesting interplay among all of these sort of the concepts, the mathematical techniques, and the measurement. So we still have this idea that regularities require very precise description prior to being given an explanation. And the explanation might be something like a unification, where you put together different precise descriptions as all hanging together by some further regularity. So this will get challenged a little bit, like really, are you explaining or are you just like giving another law that supplants the earlier laws? And we have the term law being used in multiple ways here, corresponding to what we might now call laws, or that we might call causation, in some cases corresponding to what we call mathematics, and to mechanisms, as we'll get to in the last video, but really it's highlighting the role of generalization in the sense of connecting otherwise disparate things and allowing the researcher to move between these areas, and of conveying the fact that there's some kind of degree of necessity associated with this. It's not merely an accident. All right, so then we get to the 20th century. There's three major developments then that sort of really complicated our understanding of laws. I apologize, my autocorrect does not like the word inter alia. It's supposed to be inter alia. New analytic approach to philosophy, and we're going to take a quick look at Bertrand Russell. There's a new approach to philosophizing also called pragmatism. That's going to come in the third video instead of this one. And there are massive developments in physics, especially in terms of special and general relativity and quantum mechanics. And we're going to talk a little bit about that in the second video, where there's no expectation that you actually know any of the mathematics or the physics itself. But there's something about the interplay between making the breakthroughs in physics and coming up with the right mathematical language that becomes really interesting in the early 20th century. So that will be in video 2. Okay, saving the pragmatism. I want to get us by the end of this video to an understanding of why it is that everyone got very disillusioned with laws somewhere around like the end of the 20th century. So we get to the 20th century, and Russell really sets the stage for us by this paper that has recently become read more often, called On the Notion of Cause. And there's two sort of important takeaways that he has here. One, he wants to say that cause plays no part in physics. So it's just functional deterministic equations that are relating the real quantities that are out there. What do we need this notion? Like, they never use the word cause. And he wants to say that the causality discussed by philosophers is the relic of a bygone era. And it's not even just neutral, it's sort of actively harming our discussion. So we should really move on from causation the way we should move on from the monarchy. Neither of which we've apparently done. Okay, so the causality that he was talking about being discussed by philosophers was also called the principle of causality, and he talks about this. And it's a kind of metaphysical principle. So, and it's a metaphysical principle that dates, several hundred years back at least, in the discussions in natural philosophy specifically, where it's a certain kind of commitment to the task that one's engaging in that's prior to any kind of specific empirical consideration. So it's not something that you check to see, oh, does the principle of causality hold? It's something you're like, no, I commit to the principle of causality holds, because how could it not? And therefore I can use it. So the idea is just that for everything that happens, there was some cause why it happened thus and not otherwise. So if it happened, something caused it to happen, and something caused it to happen this way rather than some other way. And we should be looking for that. So in that sense, it sounds kind of innocuous, but also maybe strong, because it then gives us methodological exhortations that if we've gotten to a certain point where we're like, well, we can explain that this was a very probable thing to happen, but not that it must have happened, then according to the principle of causality, we're not done yet. Like we have an incomplete explanation, and we should finish looking for the rest of it. So even though it's this sort of background metaphysical commitment, like, oh, whatever happens, there must have been a reason why it happened. Something made it happen. Sounds tautologically true. It still has these further downstream implications for what we should be doing in an experimental context. So as a quick terminological note, this isn't about causation as we now use the term. So we'll get to this in the third video. There have been huge and really exciting developments in causation, especially in the last 20 years, that have massively shifted the meaning of the term. Also, the term is used interchangeably in a especially confusing, historical coincidence. So causation and causality in this sense don't mean different things, although it's worth distinguishing between causality and the principle of causality, because the principle of causality is a version of what also goes under the heading, the principle of sufficient reason, that there's always a sufficient reason that something happened and happened thusly and not otherwise. And so there was some movement away from the term reason as potentially implying like an agent that has reasons, and made it into something that was more mechanical in character. So the principle of causality is more mechanical than reason. But it's still that kind of principle that he's talking about when he says that it's the relic of a bygone era. And what's really interesting is he says, it's a relic of a bygone era, we should replace it. And instead, we should just have determinism as conveyed in functionally expressed laws, drawing from the sciences, because, yeah, these are descriptions that may be phenomenological or fundamental, but there's nothing further or behind them. And what he's saying should replace causality is about to be called causal. So when he's doing it, this is, there's functional equations. He's using this for deterministic. But when we get to the very next thinker, we're going to call these causal laws specifically because of this. Okay. And this principle, despite Russell's best attempts to get people to give it up, it did not get given up at all. And the very famous quip that Einstein gave, he was very dissatisfied with quantum mechanics because there were all these probabilities. Like, why did it turn out this way? Well, it could have turned, there's a 50-50 chance it was going to be one of these two options. And he's like, no, God does not play dice. If you're not giving us the rest of the explanation, then your theory is incomplete. So he thought that quantum mechanics was incomplete because he was essentially holding to something very much like this principle of causality. So it definitely played a role in the sciences. So the other issue is he wants to say there's no use of the word cause in physics. And he really wants to separate the notion of cause from law and highlight laws as what's doing the work for conveying necessity in physics. And we're noting this here because it really does give causation a bad reputation for a long time. So in this sense, I disagree with many things in Russell's paper, but it's worth noting that what he's talking about when you actually read the paper bears very, very little resemblance to anything that goes under the current discussions of causation. But it does let us then make a sort of helpful further distinction in terms of thick versus thin causal terms. So thin causal terms are ones like the rock caused the window to break, because it conveys that there was a causal relationship between the rock and the window breaking, but it doesn't say anything else about that. A thick causal term might be the rock crashing into the window caused it, or the rock crashing into the window shattered it. And then the crashing and shattered are thick causal terms because it's saying more about how it crashed and what it did to the window. Or the rock that ticked off the window left a hole. And then you're saying more about the nature of how the window broke, then you're saying something that allows you to distinguish between it has a hole versus it shattered. So thick causal terms don't involve the word cause, but they are the terms that in a more descriptively enriched way convey causal information. Whereas a thin causal term just conveys that there was some sort of causal connection between them. All right. So we once again have Russell sort of giving us this worldview where there's just physical laws and things are sort of like deterministically settled across this manifold of events, and that's it, nothing more. All right. So this then brings us to sort of one of the last big points that we need to look at in the potted history, and that's what's called the deductive nomological model of explanation. So this originally came out in 1948 with Hempel and Oppenheim, and it really set the stage for a very, very long time. And some of what it did was introduce some important terminology. So we're going to go through that first. So part of it is the explanandum, which is that which is to be explained. We've got the explanans, that which is doing the explaining. So you've got, here's the thing to be explained, and here's the explanans that explains it. And then the explanation is a logical deduction from the premises that are the explanandum to the conclusion, or excuse me, the explanans to the conclusion, which is the explanandum. So you have this way of dividing it up and then saying of these are premises, and then you logically deduce, and it is the fact that you can deduce the explanandum as a conclusion from these premises that is what explanation is. So there's specific constraints on the premises that are allowed to figure in a deductive nomological explanation. So you always have to have some premise that's called a universal or a covering law. So it's often called the covering law. I'll be referring to it that way. Like all F's are G's is a covering law because it's just universal. It covers all F's and G's. Well, not all G's, but all F's are G's. The second premise situates the conclusion, the thing to be explained, under the covering law. So all F's are G's. This is an F. And sometimes in less simplified examples, you need much longer chains of deduction. But it's important to note they have to be deductive, not inductive. And then you get to the conclusion, this is a G. So if you want to explain, oh, look, I have this G, how can that be? You say, well, it's an F and all F's are G, therefore this is a G. So that's sort of the model of what explanation looks like on the deductive nomological model. So they call these covering laws also causal laws because they are universally quantified and sort of deterministically true. That changes what gets to count as a law. So it turns out, it's very hard to take some genuinely interesting mathematical laws and turn them into logically formulated laws of exactly this kind. So they're no longer straightforwardly mathematical. If I have a system of differential equations that I can use to calculate some quantity, it doesn't fit in there in the most natural possible way where anything is identifiable as a covering law. So there's clearly deduction going on, but there's not covering law. And part of what this does is it really shifts what gets to count as a law. So there's no more like laws about how falling bodies move. There's no presupposition that anything might be particularly fundamental. One of the commonly used examples is all ravens are black because it just fits the form all F's are G, where ravens are the F and black is the G. In fact, most, if not all, phenomenological laws wouldn't count as a covering law because they're insufficiently universal. So they're specified with respect to some specific range of phenomena, as a result of which they don't count as covering laws. They don't cover enough. All right. And the other thing that happens is that for a covering law, there's no reason it should end up describing like consistent or coherent patterns as phenomenological laws do. They're not apt for unification. So you might have a whole bunch of covering laws that really don't set you up to make some meta covering law of the covering laws. And so when you can include anything that's just a true universal generalization, then you end up with things that don't necessarily lend themselves well to doing more science. And they're very top down. So this is a G. So you explain more specific events by situating them under something more general. And there are cases where you can situate this specific happening under a somewhat more general covering law. And then that law can be situated under a more general law that holds over it. But it's always going from the top down that you get the explanation. So you have to have something that covers it in order for it to be explained. This is going to be in contrast to the way in which we see biological explanations coming, for instance, when we get to the third video. All right, called causal laws because they're universally quantified. And it's a contrast specifically with statistical laws, which can figure in what they call inductive statistical explanations. If you say 80% of F's are G's, and this is an F, so probably this is a G, you can get most of an explanation out of that, they thought. So maybe this is an F and it's a G, and 80% of F's are G's. You've gotten, something. You're more satisfied than you were before. But those kinds of explanations involve induction, not deduction, because they're sort of raising the probability of the explanandum's occurrence, but not all the way. And they were really taken to be incomplete. So they're sort of stand-ins because we don't have what we really want. In the meantime, we will make do with these inductive statistical ones while we try and get better so that we can get that probability to 100% and thereby sort of move into the realm of deductive nomological laws. All right, so this is really important because of the specific kinds of dissatisfaction that people had with the deductive nomological account. So part of it was that the modal force just didn't seem to be there in the way that laws had always, up till then, had some modal force. So the laws had to be universally true, but they could turn out to be universally true for accidental reasons. So there's a classic example where you contrast these two statements. So both of these fit the form of a covering law that you could use in the DN model. However, we think there's something about the uranium law that has more necessity associated with it. You couldn't do that. It's not just that there are none, there couldn't be any. Whereas there are no gold spheres, but there also could be. And that difference is entirely invisible on the deductive nomological account. And so here, of course, you have some people who bite the bullet and say, no, it just doesn't need to have any of that content whatsoever. And other people who say things like, well, this is a really good reason to reject it because that was the whole point of having laws, as opposed to just true generalizations, is that they were supposed to have this kind of modal content to them. Yeah. You also have the modality that was associated with laws converted to the logical connections among premises and conclusions. So as we just saw in the previous one, you're sort of offloading. So the interplay between the description and the thing being described and where you sort of locate the necessity is now entirely on the side of the words. So the world is just a thing that you describe in statements that are true or false, and that's it. Over here, you have necessity, but it's now entirely of a logical format. So you've really sort of changed the game. It's no longer about anything in the world. It's simply about these relationships among true propositions in arguments. And a lot of people thought, really, what you're doing in a deductive nomological argument is describing things, but you're not explaining it. All right. I'm only going to briefly touch on this. This does connect to the issue of, for instance, natural kinds in a very interesting way. But there's this famous term GRU, where even once you figure out how you want to like add some caveats to what your covering law is, there's no way that you can stipulate that those variables that sit in there, like the F and the G, actually aptly carve up the world in the way that you would like it to be carved up. So you could say, you know, all emeralds are green, or you could say all emeralds are GRU, and GRU is described as this weird, awkward combination of green up until a certain time and then blue after that. But the time hasn't come yet. So the emeralds could be green or GRU, and you can translate perfectly between these. And a lot of philosophers had the intuition that there was something deeply unsatisfying about GRU and bleen as ways of arbitrarily remixing things up, that your laws should have the better conceptual categories in them rather than the more arbitrary conceptual categories. And you just didn't have a way of stipulating that in the deductive nomological account. So you just don't have a way of ensuring that that takes place. And someone's like, aha, GRU has completely messed this up for us. You also have some issues that arise about inductive statistical explanation, namely, how probable does the argument have to make the conclusion in order to count as having explained it? And you can say, there was at least one, you know, more likely than not. And you're like, okay, is that 50% or higher? Should it make it quite likely? Should we like set a threshold of like 90% or better? But what if it, you know, more than doubles the likelihood that it actually happens? So, you know, there was only a 2% chance that it would happen, except for this statistical law that covers it. And now it's 5%. Oh, that looks like an improvement, but it's still only 5% likely. So that when it actually happens, it's still a very dissatisfying explanation because the thing doing the explaining only rendered it 5% likely that this was going to actually occur. All right. And this is an important note because the dissatisfaction with inductive statistical and trying to answer these questions more precisely, and the ways in which there's really interesting statistical and probabilistic laws that aren't on a track that will lead you to, they're not sort of aiming at deductive nomological laws, they're just aiming in a different direction. And we're putting this here because that really is aiming in the direction of causation as opposed to the laws that are more deterministic. So this was an important dissatisfaction with this probability such that developments in this are going to lead us in this new track. And it also implies that physics, and honestly, even in physics, they don't have laws that look like this most of the time. But at best, only physics is going to have genuine explanations because other sciences lack the right kind of laws. So the generalizations in biology, for example, are not going to be universally quantified and true always and everywhere. So even laws about evolution are difficult because, if you took the clock back and, ran it one more time, you'd probably get different sets of organisms that evolved. There was something highly contingent about the actual set of organisms that evolved under actually deeply contingent circumstances. So there's nothing that looks adequately necessary or deductive about what's going on in biology. And there was a lot of attention that was increasingly being paid to biology at the time. And really, you should be skeptical of any view of explanation where nothing in biology turns out to be explanatory, like maybe too strong. All right. It also implied, and this is a point that sort of plants a seed for pragmatism in the third video, that nothing, potentially nothing in current science counts as an explanation because we were really becoming more aware after Kuhn of how much theory change there is and how much revision and modification of the conceptual categories there is and will be. So if I say all F's are G's, and I've now redefined the F's slightly by changing my formulation of this law, then whatever it was that I thought was an explanation involving the all F's are G's turns out was never an explanation at all. So it had to be true, simpliciter, full stop, or it just never was an explanation. You were just wrong about it. So it could turn out that nothing that we currently have is an explanation, and also we wouldn't know. So that's it. From a pragmatist perspective, a very dissatisfying and maybe wrong-headed approach to this. All right. Oops. Okay. So when we sort of sum up where we're at in the sort of late 20th century, so like the second half of the 20th century, it looks like laws aren't that useful or common if they have to follow this model. It looks like there's lots of great explanations that don't follow anything like the deductive nomological model, that don't have anything like covering laws. There's lots of interesting developments in probability, and when that can count, and it doesn't seem to be lawful because, really it was part of laws that they involve necessity, not mere probability. And that led to a lot of sort of, what are we even doing with laws? You can either redefine what counts as a law, or you can chuck laws and do something else. So this is sort of setting us up to look forward to the next kinds of videos. The next video is going to look at why are so many of what turn out to be the most powerful laws and law-involving explanations mathematical in formulation. So one response to this was to really go back to especially physics and see what the mathematical derivations looked like, because they didn't look like deductive nomological explanations. And there's something about math that's just weirdly good. Like you could make actual empirical discoveries about the world by messing around with mathematics and making these unexpected predictions. And it just didn't seem like the rules of mathematics should be able to give us that kind of empirical traction. So there's something kind of unnerving about that. And that will be part of what we talk about in the next video. And in the third video, for the people who instead of, the second video is kind of, we reformulate laws in this much more mathematical form and then see what is it that they do for us, including methodologically. And then the third video is more, why is it that causation and mechanisms make such great alternatives to laws? And so we're going to look at what is it that causation is doing that's different than laws? What is it that mechanisms are doing as a form of explanation in biology, especially that's different than laws? How do those two things relate to regularities? And or how do laws potentially figure in causation and mechanisms respectively? So there's ways in which they can be seen to sort of be in competition. If you think it's a lawful explanation, then it's not causal, and vice versa. And there's also ways in which they complement, where if you have a mechanism, you still have to have the connections between them that are sort of accounted for, often in ways that we would describe as lawful in character. All right. That is the end of video 1.